Okay, so because the function itself is not 100% linear because of the nonlinear activation function, which is the sigmoid function, we cannot use what we typically do, which is finding the closed form solution like what we did in linear regression as well as ridge regression. So what we can do is a numerical algorithm known as gradient descent, right? So it's like this figure, this cartoon character starting from the top of the hill, and we're gonna go downhill and hopefully find a minimum point where we minimize the error or the loss function that we have designed. So I wanted to first introduce the generic optimization problem where we seek the model parameter beta that minimizes a particular function. And the assumption is that we are able to evaluate the function itself, right? So if we cannot even evaluate the function, it would be really hard to optimize something. And these things do happen, right? So for example, if you have a function that's related to maybe a chemical experiment or a biological experiment, sometimes, just evaluating the function value is not very easy to do, and you have to do an experiment. But, we'll assume that we can evaluate the function as well as the first order parameter, the first order derivative of the loss function with respect to its parameter, right? With respect to the variable that we can change so that the function will get minimized. In this case, beta is the parameter that we can control and we can change. And so we differentiate the loss function against beta. Okay, so we wanted to understand what exactly is the minimum, right? So we want to define the minimum, and we have a function value. The function is fx, and x is a function value, and x is called a local minimum of the function fx if there is an epsilon such that x less than or equal to x plus y for all y whose norm is less than epsilon. So this is kind of a somewhat involved definition. So what is it really saying is that I wanted to find x value, and I want to draw a small circle or a small sphere around this point, and its radius is really epsilon. And within this small radius epsilon, small radius epsilon, all the functional values is either equal to fx or greater than fx. Okay, if that's the case, then we know this fx value is a local minimum. And epsilon should be a positive number, but it could be like a really small number. Right, so epsilon could be 10 to the power of -6, and that's okay, right? As long as you have such an epsilon and that satisfies this condition, you are a local minimum. So the definition of local minimum really doesn't tell you, like, are you the local minimum within like 10 kilometers or 1 kilometer or 1 millimeter. That's not really what the definition tells you, right? So no matter how small the neighborhood is, as long as there is one such neighborhood where you are like the smallest value in it, and you are a local minimum, right? So there's once a joke that somebody put a Twitter signature or something that his the local maximum of handsomeness within a particular radius, and and without specifying what exactly is that radius. Anyhow, sorry for the nerd jokes. We'll look at the global minimum. The global minimum is really across the entire domain of the function, right? So for all y in the domain of this particular function, the fx value has to be less than or greater, less than or equal to the function value fy for y, right? So this is truly the global minimum. It has to be really the smallest value in the entire domain of fx. So on the diagram, we have, local minimum and another local minimum here, and we have some global, we have a global maximum here, and we have a local maximum here. So, so that gives you kind of a definition of things. Okay. So it's pretty easy to see that the global minimum must also be a local minimum, but the local minimum may not be a global minimum, right? So if you have a function that has a single minimum like that, and it's typically not too difficult to find, right? So, but if you have like a function with many different local minimum, and finding a good local minimum could be a problem, right? For example, if you find this local minimum, this is truly a local minimum, but its function value is actually pretty large as compared to some other local minimums who may not be the global minimum, but are also pretty close and perhaps are acceptable solutions to the optimization problem. Okay, so we really wouldn't talk about convexity and convex optimization too much. So this is like the only thing, the only place where we just talk about its definition. So a convex function is a function that satisfies these conditions. If you have 2 points on the function, that's fa is this point, fb, that's this point, and if you draw a straight line between fa and fb, so we have a line segment here, and the line segment is characterized by this function kfa plus 1 minus kfb, where k is between 0 and 1. Okay, so if you have this line, this particular line segment, and if you look at the function values between fa and fb, which is to say f bracket ka plus 1 minus k times b, and that's this value, and the corresponding function value is the red dot on this curve. And if you compare this line segment and this portion of the function, and then you will see that the line segment always lies above the functional value. Okay, so that is to say, the line segment connecting fa and fb always lies above the function itself between a and b. So this is the definition of a convex function, and if the function is convex, like you can choose this should be true for any a and b within the domain of fx. Okay, so we should understand this is how we should understand a convex function, and it is a function where any local minimum is also a global minimum, and that's a very nice thing if we wanted to find minimum, right? So that's good. So it turns out logistic regression does have a convex loss function. So its optimum is pretty easy to find, but deep neural networks typically do not have convex loss functions, and it can be pretty difficult to optimize. But that is for another lecture, and we will discuss optimization in more depth. Okay, so for the purpose of today, we're going to introduce the gradient descent algorithm, which contain a particular loss function, which is for a loss function, and we have a initial position beta 0 where optimization starts from. And the algorithm goes like this. We're going to repeat the following 2 steps over and over again until a predefined number of iterations has passed, or until the model, until the function value stops changing very much. Okay, so if the function stops changing, we would say, the function has converged. The optimization has converged. So the idea is to move in the direction of the negative gradient. So we have the current beta value, which we would call beta t minus 1. And we have the gradient value, the derivative of L computed with respect to beta. So differentiating L against beta. And this derivative is evaluated at the position beta t minus 1. Okay, so this is the gradient. And we multiply the gradient by a constant eta, known as the learning rate. So eta is probably rather small, but is greater than 0. Okay, and we're going to subtract the product between eta and the gradient from my current beta value, beta t minus 1. And this gives me the next iteration of beta. So that's the next value for beta, called beta t. Okay, so why do we subtract from, why do we subtract the gradient from the current value? And this is kind of an intuitive illustration. Okay, so let's say we are here. This is our starting point, and we wanted to get to the minimum. I think it's probably somewhere here. All right. So at this point, epsilon 2, the gradient is really, for this 1D case, the gradient is really the kind of the slope of the straight line, of the tangent line, that is tangent to the function curve, right? So this is really the tangent line. And we can see that, because this angle is positive, or is below 90 degrees, the gradient is positive. Okay, so that means in order to get to this minimum point, which I'm going to call maybe beta star. So in order to get to beta star, I need to move to my left. And in order to move to my left, I need to subtract the gradient. Alternatively, if I am at this epsilon 1's position, excuse me, if I'm at the epsilon 1 position, the gradient here will be negative, but my optimum point is to my right. So I need to move to the right, and therefore I need to subtract the gradient. Okay, so I'm going to do this over and over again. Every time I move to a new point, I will evaluate the derivative at that point, and I will subtract a small portion of the gradient, and I'll subtract a small portion of the gradient from my current model parameter beta. And this will produce a sequence of beta going from the initial position to the next one to the next one. And after t iterations, I get to beta t, right? So ideally, this should go increasingly closer to the optimum value. So if when we spend an infinite number of steps, when t goes to infinity, then the beta t goes to the optimal value beta star, and we can say this sequence converges to beta star. Okay, so what we did so far is to look at 1D functions, but in reality we deal with pretty high dimensions. For neural networks, there could be like billions of parameters. So we wanted to imagine, or at least imagine things in 2D, which hopefully give us some intuition about things in even higher dimensions that we cannot quite visualize. Okay, so we have, in 2D, we have loss surfaces. So this is one input or function parameter, then let me call this beta 1. And this is another parameter, and I'm going to call that beta 2. Okay, and I wanted to, on this 2D surface, I wanted to be able to show how big the function value is. Okay, and I'm using those diagrams that are called contour diagrams. So on this diagram, each line indicate the same function value, right? So for example, if I'm going to take the green line, and the green line goes like this, that means if this beta 1 and this beta 2 value, they have a particular function value, and that is the same as this point and this point and this point, right? So all the different points on this curve have exactly the same function value. And often the value can be read off from the diagram as well, right? So if I zoom in, I can see that this is 0.9. Okay, and by looking at the numbers, we'll see that, if I move a little bit that way, this goes to 0.6. And if I keep moving, it goes to like 0.0, negative 0.6, and negative 0.9. So it seems like if I move in this way, there's probably some kind of local minimum in here, right? So within the circle of the negative 0.9. Okay. So I'm trying to kind of put a red dot on all the local minima on this diagram, and they are kind of here, right? Because the function values kind of decrease this way and this way and this way. So there's going to be some local minimum there. I don't know exactly where, but I think the red dot is roughly where things are, right? And if you look at things this way, if you go in this direction, the functional values also decreases. So there's probably a local minimum somewhere here in this orange area, though there aren't too many lines here, so I'm not 100% sure, but probably there's going to be some local minimum there. Okay, so how do we read these contour diagrams? And I think it's important to say a couple words about how to read these things and consider where the gradient directions are. Okay, so these are known as contour diagrams, also known as level sets. So the level set is the idea that I'm going to take all the function values, all the function input x, whose function value is equal to a particular number a, right? So this set basically contains everything. For example, if this is, if my function value for this circle is 0.1, then L 0.1 f would be the level set that contains all the input x whose function value is 0.1, and that would include everything. Oops. Everything that is on this big circle, right? So everything here. Okay, so this is the level sets. Okay, and if you think about it, if I move by a little bit on this level set, so the way I move is to move along the tangent direction. So from here, and if I move like a tiny bit along the tangent direction and infinitesimal amount along the tangent direction, then my function value really shouldn't change, right? Because everything on the level set on the great circle should have the same function value. So if I move along this tangent direction for an infinitesimal small amount, then I don't change my function value. So alternatively, the intuition would say if you wanted to increase your function value or decrease your function value, then how should you move? You should move in a perpendicular direction. So either this way or that way, either to your left or to your right. But that should be the direction along which the function value changes the fastest. That could be increasing the fastest or decreasing the fastest. Okay, so therefore, the gradient direction is the direction along which the function value changes the fastest. Okay, if you constrain how much you can move just for a very, very small step, for an infinitesimal step. And along the level sets, the function value does not change. Okay, for a differentiable function, fx, the gradient at any point should be either 0. So if it's 0, we say there's no direction, and it's 0 going to be at the local minimum, the gradient is going to be 0. But if it's not 0, it will be perpendicular to the level set. Okay, so I'm showing all the arrows, and then arrows indicate the direction of the gradient, and the size of the arrow kind of indicates its magnitude. Okay, so we have some big arrows here and have some tiny arrows here. Okay, so basically as we get to the maximum or the minimum, typically the gradient magnitude becomes smaller. And as you go away, you go further away from the maximum or the minimum, the magnitude of the gradient will increase. Okay. So that's how we read these diagrams. And after that, we learn how to read these diagrams, we can perhaps understand the behaviors of gradient descent somewhat more intuitively. Okay, so we have gradient descent. If we want to perform gradient descent on a convex function, and we have the learning rate eta, which determines how much we move at each step, right? So technically, also the norm of the gradient as well as the learning rate eta both determine how much we move. We don't want to at any point, we don't want to move too much. Okay, and the reason for that is that gradient is only a local approximation of the function, right? So it's how much the function changes when you take an infinitesimal step. Okay, if you go too much, then this direction may not be the right direction. For example, if you start here, then if you take the perpendicular direction, this is kind of where the gradient is pointing to. So you can move a little bit along that direction, and that will decrease your function values. But if you move too much, let's say you move by a lot and you reach this point, it may not increase or maybe even decrease. So it may not decrease, but may even increase the function value. That is because the gradient is not a good approximation for the function over such a large interval. Okay, therefore, we typically want to use a pretty small learning rate in order for gradient descent to be effective. However, we also don't want to take very, very small learning rate. And as you can see on the diagram on the right, if I take some very small steps, I will have slow convergence, right? So because I move so little, it would take many, many steps. Let's say if the local minimum is right here, I would have to take maybe dozens or hundreds of steps before I can reach the local minimum here, okay? On the other hand, I also don't want to use a learning rate that is too large, as I'm illustrating using these red arrows. And if I'm going here and starting from this position, if I go here, because clearly this point, let me change to a different color. Clearly this green point is between the contour line of 190. So its value is somewhere between 190. And if I use a very large learning rate, I may go here, whose function value will be greater than 100, and I end up increasing instead of decreasing the function value. And that is not what I want, right? So if you use a too large a learning rate, you may see something like oscillation. So the function goes from maybe a small value to a larger value to an even larger value, which is like oscillation or overshooting behaviors. Okay, so we wanted to have really not a too big a step, nor too small a step, and want to take a medium-sized learning rate, and that would be a good step. However, as we see, as we move closer to the minimum, the good step could be smaller, could be getting smaller, right? So because here, I am pretty far away from the local minimum here, and I can't afford to make some imprecision. I could afford to have some imprecision in where I'm going. And in most directions, if I go here, if I go here, if I go a little bigger, if I go a little smaller, I don't need a lot of precision, and it can still manage to decrease the function value. However, if I have something that is, if I start from a location that is really, really close to my local minimum, then I really cannot make too much mistake before I end up increasing the function value, right? So as we move closer to the global or the local minimum, we wanted to decrease the eta value so that we avoid overshooting. Okay, so that is basically the story behind logistic regression. So as a recap, we still follow the supervised learning recipe. We started by collecting some data, x1 at y1 all the way to xn yn. We specified a model, and it's very similar to the linear regression model, except that we use a bit of a non-linear activation function, and here we use the sigmoid function. We have defined a loss function, that is the cross entropy, and we have discussed why do we wanted to minimize the cross entropy, and we presented kind of an information theory perspective on how the cross entropy works. And we also talked about gradient descent, which is the method for finding the optimal parameters that would minimize the loss function. Okay, so that basically concludes our discussion on logistic regression, which is like a single neuron in a gigantic neural network. A single neuron is still very limited, and it only works well when there is a straight line that can separate these two classes, right? So the decision boundary, as we mentioned, is still a straight line. So in this case, you have multiple straight lines that all work equally well, at least on the training set. Okay, so I've drawn 3 lines, and they all separate the training data perfectly. But there are cases where a straight line will not work as a very good decision boundary, and this is a well-known example, the XOR function. Okay, so the XOR function takes on one value when the 2 inputs are the same, and it takes on another value when the 2 inputs are different. Okay, so this is the XOR function, and it turns out that there's no way for you to separate these 2 classes of points with only a straight line, right? So you can draw any straight line you want that will not perfectly separate the the green squares and the pink circles. Okay, so that turns out, this looks very intuitive, but that was a major finding in the year 1969, when 2 famous researchers, Minsky and Papert, published a book, and where they showed that this is an impossibility. And that was a major factor in the first AI winter, when people thought, all these AI techniques, like neural networks or logistic regression, they really don't work, right? Because they don't even work on such a simplistic case. How can you expect this to really be applicable to the general problem of artificial intelligence that has to be a lot more difficult, right? So that was a challenge. And obviously, we now have techniques that can do that. And one of the possible solutions to that is known as a MLP, or a multi-layered perceptron. and we will talk about MLPs in our next lecture. So that ends this lecture. Thank you for watching.